So now basic counting principle. The first basic counting principle is counting by enumeration. Enumeration basically means you use brute force. List all possible outcomes one by one. This is the most naive, inefficient method, but this is also the easiest one. Okay, this should be used as the last resort. So for example, how many ways to form a length 1 string from alphabet 1 to 7? So let me explain some terminology. Alphabet means a set. Okay, let's say it's S, that I have a bunch of things. I can pick the thing inside to form a string. That means a symbol, a list of symbols. And length 1 string means the string have only one digit, or one alphabet, or one letters. So here, my alphabet is 1 to 7, and I want to have a length 1 string. You can think of this as I have a placeholder, I have a box, I can put things inside. How many ways can I select one thing from this set? Well, there are 7 objects, right? So therefore, it is just the set of 7. So in this case, I'm saying my selection set is 1, 2, 3, 4, 5 up to 7, and totally this set has 7 elements. Example 2. How many ways to form a length 3 string from alphabet 0 and 1? So in this case, I can select 0 and 1 to what? To put in 3 boxes. So I have a box of length 3, and I can put 0 and 1 here. And the question is asking, how many ways can I approach this? So you can think of it like this. So for the first box, I can put a 0. The second box, I can also put a 0. The third box, I can also put 0. That means I have 0, 0, 0, this guy. Or I can put 1 in the last box, so I have 0, 0, 1. So what are these? This is basically like I put everything as 0, and then I put 1 once in here, in the last box, the middle box, and the first box. So that means this is all 0. These 3 are, there's only 1, 1, which is in whatever location. These are what? They are 2, 1, and I put it in this location. And lastly, all of them are 1. And how many of them? There are 8 of them. So this is by listing all the possible cases to count the possibilities. And then let's say I have to form a length 3 string from alphabet ABC. So in this case, I have 3 boxes again. And I can pick ABC in these kind of boxes. So for example, I can put AAA, so I can put AAA, and then I can change the last A to B, so I have AAB, and then I put this B to the second box, I have ABA, and then I put this B to the first box, I have BAB, so I get this, and then I can also do AAC, ACA, CAA, and then so on. And you quickly realize, oh no, if you do the brute force, it will be forever. So we need a better way to do this. So a better way to do this is to visualize the whole thing. The whole process can be visualized using a tree. So what is tree? You are a computer science student. Please think in a computer science way. Whenever you count, please imagine a tree in your brain. Okay. So what is a tree? A tree is a cyclic connected graph. We will explain this terminology when we talk about graph theory. So basically, a cyclic means there's no cycle. Connected means every node is connected. There's no isolated node. Graph means something that looks like this. We will talk about it later. So in this case, so we have 3 boxes, and now I represent them with 3 question marks. So the question is, I have 3 boxes, I can put letter A, B, C here, right? So we will look at the box one by one. For the first box, I can put A, or put B, or put C. So I have 3 branches. I have 3 branches. So this is meaning that I now fill in the first box as A, the second box as B, the last box as C. And then now I look at the second box. I can have 3 branches again and put A, put B, put C. And lastly, for the last box, I also have 3 branches. So from this process, you see a pattern. Every time when I branch, I have 3 ways to branch. And how many branch? 3 branch. And how many times I branch? 3 times. So I have this thing. So in the end, if I count, there are 27 possibilities here. That means this is what you get if you brute force all the possibility, which is 27. And it's actually 3 times 3 times 3. The 3 correspond to 3 branches, and the dot here correspond to multiplication, which correspond to how many times you branch. Here's a generalization. Suppose we have length k string in an n set. That means suppose I have 1, 2, up to n. This is my alphabet, and I want to put it into k boxes. How many ways can I put it? This will be the answer. Okay? And how is this? So basically it means each time when I branch, I have n branches, and for each node I can branch n branches, and this process I can do k time. So that's why I have power k. So this is the simple illustration. So for specific illustration, let's consider the following example. Suppose I have 1 to 7. Okay, this is a mistake, so this 5 is a mistake. And then what's next? How many ways to form a link 4 string? Well, this is number. Every time you branch 7 times, and you branch 4 layers, so 7 to the power 4. This is the number. Okay. Product rule. Basically, it's just Cartesian product. Choose one of A, B, C in a set P, and X, Y in set Q is the same as we choose the Cartesian product in this set. So the number of elements in a Cartesian product is basically the product of their own cardinality. So here's a very simple example. Suppose you have breakfast, pancake, bacon, egg, bagel. Lunch is burger, fries, salad, macaroni, pizza. Tea is steak, pasta. So how many daily diet of B, L, D can you have? So basically it's this. Okay, B times L times D. If you want to list out all the possibility, you have to write a very big set, so which I'm not going to do. But if you use the product rule using Cartesian product, you will know that by product rule, it's basically set of B, set of L, set of D, which is 3 times 4 times 2, which is 24. And if you want to do this by a tree, so for breakfast, you will have what? Pancake, okay, pancake, and then bacon and egg, and then bagel, so bagel. And then after that, you start lunch. Burger and fry, so you have burger and fry, and then burger and fry, and then salad, so salad, and then macaroni pizza, and you see, and then every one of them have 2 branches, and you see the tree become very big very quickly. So brute force is not the clever option. Avoid brute force. Here are more examples for product rule. So suppose I have a link 4 string from 0 to 9. Do not begin with 0. So again, I have 4 boxes. I can put any number inside, but this guy cannot put 0. Okay, so how do we count it? So I call this A1, I call this A2, I call this A3, I call this A4. It will be the number of string is just the Cartesian product of A1 times A2 times A3 times A4. By product rule, then it will be this. Then box 2, box 3, box 4 can be any number. So there are 0 to 9, there are 10 choices. Box 1 cannot be 0, so there are only 9 choices. So I will have this number, which gives me 9,000. The explanation is here, okay? So this is also the number of 4-digit positive integer with no leading 0. Usually you write 1, 2, 3, 4 or 0, 2, 3, 4, but you don't write 0, right? You just write 2, 3, 4. You don't write 0, 7, 1, 7, right? You just write 1, 7, okay? 7. Something like this, okay? Now here's another example. How many length through string over the alphabet 0 to 9 do not have repeated digit? So you have 2 boxes. Each of them can store 0 to 9. Okay, but this box cannot store the number that have already stored in the first box. So the first box have 10 choices. The second box have to minus 1 because the 1 choices used by the first box, you cannot repeat it. So there's only 9 choices. So 10 times 9, 90. Okay, how many length 4 string over 0 to 9 do not have repeated digit? So again, you have 4 boxes. First box, you have 10 choices. 0 to 9. Second box, you have 9 choices because one of the digit has been used here, so you cannot use that one. Otherwise, it's repetition. And then, by the same logic, so now we are going to talk about sum rule. After product rule, we are talking about sum rule. So sum rule actually is a special case of inclusion-exclusion principle. So basically, what is sum rule? Sum rule is saying that if this guy is empty set, we don't see it, and this is sum rule. Okay, that's simple. So this soup salad is a very simple example. Let's talk about a harder one. So this one is interesting. So suppose A is 1, B is 2, 3, C is 3, 4. What is A or B or C? There are 3 approaches. So let's say I have A or B or C. So I will have 1, okay, 1, or set 2 is 2, 3, 2, 3, and then or 3, 4, 3, 4. So I will do like this. So I will evaluate A or B. So it will be 1, 2, 3, and then or 3, 4. And then what I do? I will evaluate this. It will be 1, 2, 3, 4, something like this. And then here's the thing. This seems very trivial, and then therefore, if you take the bar, it will be 4. Okay, here's the thing. Whenever you evaluate these 2 sets, you have to compare: is this guy appeared here? 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 And is this guy appeared here? So there are many comparisons you have done in your brain, and you just didn't notice it. And in fact, this approach 3, construct A or B or C, is the most naive, inefficient way, so you should avoid. So let's see what can we do in another way. So let's talk about approach 1. We try to use inclusion-exclusion principle. So we use the inclusion-exclusion principle for 3 sets blindly. So we first know that A or B or C inclusion-exclusion principle give us this thing. So now we have to compute this thing. What's A? A is single element, so 1. What's B? B have 2 and 3, so 2 thing. What's C? C is 3, 4, so 2 thing. What is A and B? We have to compute what's A and B. A and B have nothing in common, so empty set. Okay. What is A and C? A and C have nothing in common, so empty set. What is B and C? B and C, the common thing is 3, so single and 3. What's A and B and C? Empty set. Okay. Then we have 1 plus 2 plus 2 minus 0 minus 0 plus minus 1 plus 0, which give me 4. Okay. In this particular process, how many evaluations have I done? I have to compute this guy, I have to compute this guy, I have to compute this guy, and I have to compute this guy, which is 4 computation that consume my brain power. Not good. Let's look at this approach. If I split this set like this, what happened? Now I have 2 sets, A and B. Okay, then I can use inclusion-exclusion principle. This is my A, this is my B, this is my A and B. Okay, so now with this, I have to evaluate. Okay, what's A? A is just 1. Okay, what's B or C? So this one I need to evaluate. This again by what? Using exclusion-inclusion principle. This thing. Okay, and then what is this guy? A and B or C. So A and B or C. So I will distribute it inside. So I will have A and B or A and C, right? Okay, and then we know these are all empty set. Therefore, we have this. Okay, and then what's next? This yellow thing, I can give it like this. And then I will get the number, in the end is 4. The point I want to make here is not about the detail evaluation. It's about here, I only need to evaluate these 2 things, which the cost is relatively lower. And in fact, if I give you 1 million sets, and I want to ask you to do this kind of operation, do not do this one. And now let's talk about subtraction rule. I have a S set. And then I have a set A that is subset. Okay, so that means this is S, this is, let's say, A. A is inside S. Okay, now this AC denoted as S subtract A means what? That means anything not in A. So in this case, it's all the this is my AC. Okay, then what is the size of AC? It will be the trivially size of S minus size of A. Example: suppose I have X equal 1 to 3. How many subsets of X are possible containing at least 2, including 2 elements? So now I'm saying P2X is the power set, which is set of all possible subset, which is this. Okay. Now I want to find what? Subset of X that is containing at least 2 or more elements. What's the opposite? The opposite is 1 or 0 element. So the opposite of S is SC, which is by definition less than 2. That means 1 or 0. This is an OR, so I can write this as an OR. That means there are 2 sets containing, okay, the set containing 1 element. That means it will be, okay, I make a mistake, so it should be 3 sets. The set 1, set 2, and set 3, okay. And then this is null set, okay. And then I compute this. So what is power set? Power set is just how many elements here. It will be 2 to the power A. And then each of this set have 1 element, so there's a 3 here. This guy have what? Nothing, but nothing is an element, so there's a 1. So therefore, 8 minus 4 is 4, okay. Okay, so this is wrong. I make a mistake. It should be set 1, set 2, set 3, okay.